Good afternoon, everyone. Over the summer, Bernadette and I did research on the parameter variations with West Nile virus. We worked with the former math professor, Elsa Schaefer, and we also worked with biology students at VCU under the supervision of Susan Robertson, and they did research within the field, which was really cool. And we also worked with entomologist Kevin Calloway, and he gave us parameter advice and actual prices for our controls based off of the conditions in St. Tammany Parish in Louisiana. And we used all of this data to create a model to show the different parameter variations that would affect the spread of West Nile virus. So what is West Nile virus? West Nile virus is a disease that's transmitted to mosquitoes by mosquitoes biting infected birds. So once the mosquitoes bite the infected birds, then the mosquitoes bite us, and that's how we get West Nile virus. And it causes flu-like symptoms, and it can lead to death.
The following flowchart diagrams will help to explain the model for West Nile virus. Initially, all birds start out as nestlings, and then they mature to the fledgling compartment, and then later to adult. And at any stage, they can die of natural death. And then for the birds, we used an SIR model. So the first compartment is susceptible, and all birds are born into this class as nestlings. And then they move to the infected class at a certain rate, the rate of infection, and then they move to the recovered class at a recovery rate, and if they're in the infected class, then they can die from disease. And then for mosquitoes, we have the susceptible class, the first one, and mosquitoes are born into that, and then they move to the latent class, mosquito latent, which means that they're infected with the disease, but they can't spread it yet. And then they move to the infected class, where they can either die of disease or natural death, and as you can see in any of the classes, they can die of natural death.
And we have three methods of control. The first method of control is vaccination, which is vaccination of the birds. So as we saw the SIR model before, it works the same way. They're born into the susceptible class, and then they can move to the infected and to the recovered. But with vaccination, what happens is they skip the infected stage and go straight from susceptible to recovered through vaccination. We have control from the mosquitoes as well. So we have larvicide and adulticide. What larvicide does is it's sprayed into the standing water. So it kills basically like the baby mosquitoes, and it prevents them from being born. And we have adulticide, which is sprayed on the ground, which kills the adult mosquitoes. So when mosquitoes are susceptible, or when they're first born, that's when you use larvicide. With the larvicide control, they can die from natural death or from adulticide. And with latency in the infected stage, they can be killed through adulticide and natural death or disease death as well. Our goal with optimal control is to investigate which one of our three controls, vaccination, adulticide, and larvicide, will be the most effective and the most cost efficient at the same time.
As you can see from the model, there are many parameters that go into this model for West Nile virus. So how do we determine which parameters are the most significant? We used two methods. The first was performed by a senior research collaborator before we did our research, and it's called a sensitivity analysis, and this works by determining a partial rank correlation coefficient, or the PRCC value, and it's a number between 0 and 1. And the closer the number is to 0, then the more significant it is. And then additionally, in our group, we varied different parameters to see which parameters had the most impact on the spread of the disease, as well as the cost for control. So these were the 5 most significant parameters. The first one is the total mosquitoes in the environment, or also known as the carrying capacity. And the second one is the biting rate, which is the rate at which the mosquitoes bite the birds. And then we have the nestling infectivity, which is the probability that the mosquito will be infected after it bites an infected bird. and then the mosquito natural mortality rate, which is just the rate that they die of natural causes. And if you notice the mosquito natural mortality rate is negative. So that means it has an inverse relationship. So by increasing the value of the parameter, it actually improves the disease epidemic. And then finally, we have the nestling preference, which means as the nestling preference increases, then the chances of the mosquito biting the birds is greater. So it would bite the nestlings as opposed to fledglings or adults. And then these are some of the other parameters, but I'm not going to go through all of them because the model before control determined that they were not significant based on their PRCC values, but we also looked at them.
So we did a few things to analyze each parameter when we were testing them. The first thing we did is we looked at the change in the parameter value versus the change of the number of the infected mosquitoes. So we basically saw by how much we increased each parameter, how that affected the change of the number in the infected mosquitoes. We looked at the percent decrease in the number of infected mosquitoes. So that's kind of self-explanatory. We looked at our baseline values, and we looked at the values that we were producing when we changed the parameters and the difference between the number of infected mosquitoes. We looked at the cost of our control per 100 mosquitoes. So if the cost per 100 mosquitoes was outrageous, then we would obviously think that it wouldn't necessarily be worth it to spend that much money if we were only killing off a small amount of mosquitoes. And we looked at the change from our baseline results. So we had a baseline and we worked off of everything from there.
This is a chart that summarizes the results when changing the total mosquitoes in the environment. And if you can see on the left-hand side in the y-axis is the cost for control, and then on the right-hand side for the y-axis is the total number of infected mosquitoes. And along the horizontal axis, first is the level of control. So you have either the first none, moderate, and high. So it's just how much control we're using. And then the change in the value of the parameter. And the yellow section of the bar graph represents control with vaccination. And then the red is with larvicide, and then the blue is with adulticide. For the total mosquitoes in the environment, as it increases, then you can see that the total number of infected mosquitoes increases as well. And in the last two columns, the cost for control, it doesn't change very much. So that shows that control is necessary, but once you reach a certain point of mosquitoes, then it doesn't really affect it that much. So the control is needed, but it's ineffective once you reach a certain point. Next is the mosquito biting rate. So similarly, as it increases, as more mosquitoes are biting at a faster rate, then the total number of mosquitoes is going to increase. Total number of infected mosquitoes is going to increase. And control, again, stays about the same as the biting rate increases. And if you notice, between the last two columns, there's still the same amount of control is used, but the total number of infected mosquitoes is still over 1,500. So at that point, the control is not doing that much, so it wouldn't, it's ineffective, but control is still needed. For nestling infectivity, as it increases, the number of mosquitoes does increase, but not significantly, and the cost for control increases a lot, but it's very expensive to control just not that many infected mosquitoes. So it's expensive. While it is effective, it's not the best solution. For the mosquito natural mortality rate, this one was the one where it was negative. So when the natural mortality rate is low, then the number of infected mosquitoes is high, and control does help, and it is effective. But again, the total number of infected mosquitoes is lower. But control it's expensive, so it wouldn't be it's not necessary to spend the money to control.
So with nestling preference, we see that when nestling preference is high, the number of mosquitoes does increase. When nestling preference is at its highest, it gets towards about 850 or so, and then when we add in levels of control, we can bring it down to a little under 500. But we do see that it kind of hits a threshold, so using control is extremely helpful. It cuts it down by almost 50%. But if you look at the cost for control, it's extremely expensive, and once you're getting to that point where with the different levels of control, when you're using more and more and you're not decreasing the amount of infected mosquitoes effectively, that it becomes kind of useless to spend the money. So control definitely is needed, but it's only truly effective for when nestling preference is lower. So once it reaches a certain point, it just becomes extremely too costly and not worth it. So what we played around with a little bit is testing two different parameters at once. So we looked at nestling preference and nestling infectivity at the same time. And we looked at them when nestling preference was low and nestling infectivity was high, and when they were both high. And what we saw was that when they're both high, that the number of infected mosquitoes is extremely high. It's around like 1,700 or so, not 17,000. And control definitely is necessary. It is a little costly. If you look at the low, medium, and high levels of control, they're about the same with the number of infected mosquitoes, and the cost goes up. So it is definitely necessary, but it becomes ineffective after a while. So the PRCC, these were the predicted significant parameters, and we definitely agreed that these ones were significant. They definitely produced a high level of infected mosquitoes, and control was needed. But with a lot of them, they did reach a point in time where control just became ineffective because the number of infected mosquitoes was just too high. Another parameter that we looked at was the adult recovery rate. So here we see that when the adult recovery rate is longer, that the number of infected mosquitoes is high as well, and it becomes very costly to control. If you look at when it's 1/7, or when the recovery rate is 1 week, it takes about a little over $25,000 worth of control to decrease it, but it does decrease it under 50 mosquitoes, so it is expensive, but it's definitely effective. And I just put nestling infectivity under there because that was one that the PRCC did predict was significant. And as you can see, there's more infected mosquitoes with the adult recovery rate, and it does bring it down to a low level, so I would consider it significant as well compared to the nestling infectivity. We also looked at the natural death rate of fledglings. We saw here that there was a funnel effect. So when the natural death rate was high, or when there was less fledgling birds, there was more infected mosquitoes, just because when there's a smaller amount of birds, it's a lot easier for more of the birds to get infected. So if you kind of think about it, it makes sense. There's less of a group to get infected, so a higher percentage of the group is going to get infected, which in turn cause more infected mosquitoes. So in conclusion, we think the PRCC is a successful tool in determining what parameters are significant, but we do think there are additional parameters that aren't picked up by the PRCC. So in further research, we would think it would be interesting to determine what exactly to look at within each parameter to determine if it's significant or not. And when combining parameters, when you're combining parameters, significant and not significant, what it is that makes them significant when combined together.
And we would like to thank Dr. Susan Robinson at VCU, as well as Dr. Schaefer, who was able to be here, and Dr. Kevin Tayue, who was in Louisiana and gave us the live parameters. Thank you.
We have about 2 minutes if anyone has a question or comment.
A question?
Yeah.
Just curious, so when a mosquito survives, are they active? So if they infect?
So they were infected.
They were infected, they didn't die, and they're recovering, right? Or whatever you call it.
The mosquitoes don't recover.
They don't, because they have such a small lifespan. So like once they're
So
infected,
it's the birds that recover.
the birds can recover. Yeah.
If a mosquito mosquito bites them, can they?
So when a bird recovers, they then go back to the susceptible class. So once they recover, they do have like the opportunity to get infected again. Yeah.
Yep. Any other questions?
Thank you.
No, thank you.